Hello? Yes, guys. Are you able to hear?
Yes.
Okay, cool. So I don't think my video is required today, right? If I want it, I'll just open it and show you. But anyways, for now, I don't think the video is required. And yeah, as I told you yesterday, right? So we'll be what is that? I'll be taking 2 hours class today. And after 1 hour, I'll be giving you a break of 15 minutes, and then we'll start again, right? Is that cool? Yes? No?
Yes, sir.
Okay, cool. So we were seeing chemical bonding people. We'll directly go for it. Where is my OneNote? I closed it. Okay, no issues. I'll just open it again. Okay. Yeah. So it was just an introduction today. So I just told you that there are two types of bonds in chemistry, right? One is what is called as primary bonds. The other one is what is called as secondary bonds, right? Primary bonds is all about the permanent rearrangement, or say the complete rearrangement of electronic configuration. The electron is completely lost or completely gained or completely shared, right? And in case of secondary, it is not going to be a 100% rearrangement. It is going to be a partial rearrangement. And under your primary bonds, I have all the types of bonds you already know: ionic bonds, covalent bonds, coordinate bonds, so on and so forth, right? And under your secondary types of bonds, I have hydrogen bonding, dipole-dipole interactions, van der Waals forces, and yeah, all those things, right? So yesterday we completed ionic bonds, right? So I told you that there'll be a cation, anion, and we saw the properties, right? So they have high lattice energy, they have high solubility in water, they have high melting and boiling points, right? And I told you what are the conditions in which the ionic bond can be formed, right? The metal which is going to form the cation should have less ionization energy, and the metal, and the element which is going to form the anion should have high electron gain enthalpy, right? So these are all the things which we saw last class, right? Okay, so today we'll start with covalent bonds. Right. So we already know so many stuffs about covalent bonds, so I'm not going to go into details about this. But anyways, there are other things you have to see. Anyways, so covalent bonds we know is going to be formed by mutual sharing of electron between the atoms, isn't it? Right. So we already know how the sharing will happen. You already know Lewis dot structures. Hope you know, like hope you know what are Lewis dot structures. Like the valence electrons are represented, and then you go for octet or duplet to make sure the atoms become stable and all that. So yes, that we know. Now what we have to understand is now how is it that through the covalent bonds the atoms are getting stabilized is what we have to understand, or say, or in other words, how is it that we are going to interpret the interactions between the atoms. So in case of an ionic bond, it's pretty straightforward, isn't it? I have a full positive charge, I have a full negative charge, so it's going to be a strong electrostatic force of attraction, isn't it? But in covalent bonds, it's not like that. We'll see how it is going to happen, right? Okay, so let me start with this. Okay, so there are two atoms, right? So there are two atoms, right? And they're very, very far apart, right? The distance between them is very, very large. Okay, so I'm going to call these atoms as isolated atoms. Okay, now please understand this isolated actually makes so much sense, right? So when you want to talk about electronic configuration of an atom, okay, whenever you want to talk about the electronic configuration of an atom, the atom should be isolated in the sense it should not be in interaction with any of the neighboring atoms. It should be as much as far away from all its neighbors, right? Only in that case I will be able to speak about the electronic configuration of an atom, right? So isolated, I think the name itself makes you understand. It should be alone, right? Only then I'll be able to speak about the electronic configuration. Okay, so now what is going to happen is I am going to just push them little towards what is it, towards each other, right? And what is going to happen in that, right? So you can easily understand, people, in an atom there will be definitely the nucleus which will be at the center, right? And obviously it will have some electrons also, right? So when the atoms are isolated, that is when they are very, very far away from each other, right? so there will not be any interactions. That is understood, right? But if I'm going to just push them, if I'm just going to push them like this to a position where the interaction starts, right? Now, what kind of interaction I'm speaking about? It's very simple, right? So the nucleus of this atom and the electron of this atom are going to have some attractive force, obviously, because nucleus is positively charged, electrons are negatively charged, and same goes here also. This nucleus and this electron are going to have the attractive forces existing between this nucleus and this electron. The attractive forces are going to start existing, isn't it? Now I don't have to do anything. The atoms will keep on coming closer and closer and closer, isn't it? Because now I have put them in a position where the interaction starts. Now I don't have to do anything. The atoms by themselves will keep on coming closer and closer and closer, right? Now at a point of time, what is going to happen is they are going to become so close to each other, right? They're going to become so close to each other. Now the attractive forces are no more existing. I'm going to have the repulsive forces coming into the picture, right? So again, that is going to be unstable state, right? So when they are little far apart, attractive forces dominate. When they are very, very close to each other, the repulsive forces are going to dominate, right? Okay. Now, obviously, in between these two, that is when the attractive force is dominating and between the case where I have repulsive force dominating, there is going to be one particular point, right, where what to say, where the atoms are going to become most stable, right? Neither the attractive forces are dominating and nor the repulsive forces are dominating, right? And obviously, you can understand the energy. If I consider the energy, right, I know it is basically going to be equal to minus F dot ds or minus F dot s, the dot product of force. I would say it's work done, but still work and energy. Only the sign will change. If it's going to be energy, I'll just put a plus. Doesn't matter. Okay. So what I'm telling is there is going to be one particular point, right, where neither the attractive force nor the repulsive force is going to dominate. And that point, the atoms will have the least energy, right? At that point, the atoms will have the least energy. And obviously, we know that whenever I have the least energy, that is where I'm going to have maximum stability, right? Okay. Now, if I put all this, whatever I told you, in the form of a graph, right, this is how it's going to look, right? Okay. So I have y-axis, x-axis, right? So yeah, so in the x-axis, I'm going to put R naught. R naught is the internuclear distance, right? R naught is basically the distance between, I'm talking about, say this is R naught, the distance between the atom. And here in the y-axis, I'm going to have potential energy. As simple as that. I mean, energy of the system. In the system, in the sense, both the atoms put together is my system now. Is that cool? Right? Okay. So, say when the atoms are, now when the internuclear distance is very, very large, right? When the internuclear distance is very, very large, obviously no attractive force, no repulsive force, the potential energy will be really, really high, right? So what is going to happen is now I'm going to put them in a position where the attractive forces just starts to exist. So what is going to happen is the potential energy will keep on decreasing, right? The potential energy will keep on decreasing, and there'll be a particular distance. Like say if I put it here, like what is this? Yeah. So if I put it here, so at this point the atoms become so close to each other. See, you can see that at this way the what is it, the distance between the atoms decreases, right? Okay, hope you understand. Anyways, so at this point the repulsive forces are going to dominate. So if you're going to bring them still more and more closer, they are going to have increase in energy again happening, right? Okay, now this is the point where I'm interested in, right, where I have the least potential energy, and this is where I say the bond is formed, right? The covalent bond is formed. Okay, hope you understand, right? This is the point where I have the minimum potential energy, maximum stability, and that is where I say the bond, a covalent bond, is getting formed, right? So I hope you understand how is it that I'm going to have the attractive forces existing between the atoms in a covalent bond, right? Cool. So this is the overall part, right? Now we understood that how that like attractive forces are existing and all that we have done. Now we'll see how a covalent bond is getting formed. There are various theories, right? You know, obviously you should have known, right? There are various theories which suggest, okay, this is how a covalent bond is formed. This is how I can interpret the structure of the molecule, and so on and so forth. We'll see one by one. What are they? Is the tool, right? So we'll move on. Let's make a page. Yeah. So the first one, which explains the covalent bond formation is my Lewis theory, right? And actually, I'll be able to combine this with your valence bond theory, VB theory. VB is valence bond theory. Okay, so they are almost little, I would say, little similar, right? Okay, we'll see one by one. What is this? Okay, so for Lewis theory, we know that Lewis dot structures. For example, if it is like, I'll just give you only one example because you must have been doing this from your 9th or 8th class, right? Say for example, if I have H2O as an example, right? So how do we draw the Lewis dot structures? Right, it's very pretty simple, right? So oxygen atom is at the center. I know I have 6 valence electron in oxygen, right? 6 correct. 6 valence electrons in ox. Am I correct? Yes, correct. So let me draw it this way. Okay, and I have hydrogen atoms on both sides having 1 electron each in the valence shell. See, in Lewis dot structures, hope you remember, I have to take only the valence shells, I mean valence electrons, right? Fine. So if I look at hydrogen, for hydrogen duplet has to be satisfied. So obviously this will take these 2 electrons. Mutual sharing is going to happen. Again, same goes here, right? And oxygen requires, already has 6 electrons. It requires 2 more electrons to satisfy its octet. So the shared pair of electron is also taken. So that's how we draw the structure. So now if I draw the structure properly, it will be, right? And oxygen is going to have 2 lone pairs. Okay. See, a lot of times questions can come asking about find the number of bond pairs and lone pairs in the structure. Now, obviously, we'll understand that there are 2 bond pairs and 2 lone pairs in this molecule. So like this also questions can come. Okay, so anyways, now coming back to Lewis theory, like this is how you draw the Lewis dot structure. Now what I'm trying to tell you is Lewis theory is actually going to depend only on one particular thing. It is actually going to depend upon this octet or duplet for the stability of the atom, right? So you're saying the mutual sharing of electron is going to happen and it is going to be based purely on octet or duplet, right? Okay, again that's the only thing. So what Lewis didn't tell me, right, is that it doesn't talk about the structure of the molecule, right? What shape or what structure, what geometry, right? That and all it doesn't tell you, and it doesn't talk about the strength of the bond, right? I don't know which, say I have an OH bond, I understand. If I compare it with this, say if I have H2S, I have the same kind of Lewis structure, but it doesn't explain me which bond is stronger or which bond is weaker. All this is not told, right? And the third problem and the main problem would be there are molecules, right? There are molecules which doesn't obey octet or duplet rule, right? So that means I can have in certain molecules I have more than 8 electrons in the valence shell, or in some cases I can even have less than 8 electrons in the valence shell, right? Okay, so that these are the few if you want me to give you can you give me an example, people, where the element or the atom is going to have more than 8 electrons in the valence shell? Hope you're there. So anybody? I think there'll be a chat, I guess. Oh yeah, PCl5. Yes, very good example. So in PCl5, okay, fine. So we'll just see what happens in, okay, one more. SF6. Yes, very good, very good. Yes, all these are the examples. Good, right? So in PCl5, what happens? So in PCl5, now phosphorus has the electronic configuration of say 3. So 3s2, 3p3. So what I understand is I have 5 valence electrons, isn't it? And each of the chlorine atom is going to give me 1 electron each. So I'm going to have 5 more electrons. So that makes it 10 electrons, isn't it? And same goes with your SF6. SF6 is going to have 12 electrons in the valence shell, right? Okay. So is there any example for elements having less than 8 electrons in the valence shell? Any example for less than 8 electrons in the valence shell? LiCl, for Li, see, for Li, duplet is satisfied, is it not? Li is having 1s2, 2s2, I mean 1s2, 2s1. So the 2s1 electron is lost. So duplet is satisfied for lithium. So that is not the case. Any other example? And I would say, yeah, it is actually a 50% covalent and 50% ionic compound, LiCl. So we'll speak about it. Okay. So any other example? NO2. NO2. I think again NO2. I have 5. No, Kana. Okay, if I can draw the low charge structure, maybe you'll understand. But NO2. Okay, we'll try NO2. But I don't think it's an answer. Okay, so fine. Let me try NO2. So we'll see what happens. So for nitrogen, I have 5 valence electrons. Okay, and for oxygen, I have 6 valence electrons. Right, again, this side also. Okay, so obviously this oxygen requires 2 more electrons to satisfy its octet, right? So it's done. And for this oxygen, if I put 2 more, so basically nitrogen requires only 3 more electrons, right? So there are 2 possible structures for NO2 actually. So it will, if I take this electron also, this will become a radical. So whenever you see this single unpaired electrons, hope you must have seen radicals in organic, right? So whenever you have this single unpaired electrons in an element after the bonding is over, so that becomes a radical. Okay, but you can see there's one more structure which I can draw, and that structure actually it should be NO2 minus. That's how it will become. So anyways, so NO2 is not the answer, right? It's a radical. Okay, I'll give you the example. The example is BF3, boron trifluoride, or I can even have BeCl2, right? So all these are examples. You can understand how. Okay, I'll make a page. 1 second. Right. So in BF3, right? So boron is having 2s2, 2p1. I mean 1s2, 2s2, 2p1, right? Valence, I mean the total number of electrons is 5, right? Okay. So now what happens? Your totally I would have basically 3 valence electrons, right? So each of the fluorine atom will give me 1 electron. So I'll have 3 plus 3 will become 6. Now I have only 6 electrons in the valence shell for boron. Okay, so that again that means that I have less than 8 electrons in the valence shell. Okay, the same goes with my BeCl2. So beryllium is gonna have 2s2, correct? Yeah. So 2s2 is there. 1s2, 2s2, atomic number 4 for beryllium, right? So 2s2 is there. So again, each of the chlorine totally there are 2 valence electrons, and each chlorine atom is going to give me 1, so it becomes 4 valence electron. Again, less than 8 electrons in the valence shell, right? So these 2 are the examples for less than 8 electrons in the valence shell. And people, whenever you see this kind of thing happening, that is, whenever a central element in a compound is having less than 8 electrons in the valence shell, they can act as dash. Any answers? BCl3, yes, good, Aditi, yes, correct. So now I'm not asking is, when I have less than 8 electrons in the valence shell for an element in a compound, they can act as dash.
Electrophile.
Electrophile. Yes, good. Electrophile is the answer. Any other? Good, good. This I didn't think of. Good. Okay, anything else? So you're stuck. Who said that answer? Aditi, is that you?
Sir Sriharini.
Oh, Sriharini. Okay, so Sriharini, I think you're stuck in organic yet. But good. Yes, they can act as electrophiles. Good. Any other thing?
Sir, acids.
Sorry?
Sir, acids.
Ah, yes, yes, yes. Not just acids. Sanjana is giving a perfect answer. It is Lewis acid. Yes. Right? So yeah, they can act as Lewis acids. So we know what are Lewis acids. Lewis acids are the one which will be able to accept a pair of electrons. Right? So since their octet is not satisfied, right? So these kind of molecules can act as Lewis acids. That means it will be able to accept electrons. Okay, cool. Yes. Okay, so we'll continue. So these are the problems with Lewis theory, right? So it doesn't give me the structure. It doesn't tell me about the strength of the bond. It doesn't talk about the magnetic properties. It doesn't give me the explanation for these kind of molecules where I have less than 8 electrons, more than 8 electrons. All these are not explained by Lewis. Okay, so fine. So now when I go for valence bond theory, VB, right? So I want you to take a statement for valence bond. Please take the statement for valence bond theory. I'm going to read the statement. Right? So it says a covalent bond is formed. A covalent bond is formed when unpaired electrons, when unpaired electrons in the valence shell of the atom, when unpaired electrons in the valence shell of an atom gets paired. Okay, that's what it says. Again, I'll repeat the statement, right? So valence bond theory says a covalent bond is formed when the unpaired electrons in the valence shell of an atom gets paired. As simple as that, right? Okay, so I think this makes sense. If you just take some examples, you'll clearly understand what I'm trying to say. Say I'll take H2 molecule, the simplest of the one. So if I take H2, I have hydrogen having one S1, another hydrogen also having one S1. So you can see there is unpaired electrons in the valence shell, right? So a covalent bond is formed when they come together and they become paired, and I have one one covalent bond formed between the hydrogen atoms, right? The same goes with oxygen. If you take, say, oxygen molecule, if I take oxygen, I have one S. Okay, I'll not write the entire configuration. I'll just write the valence configuration, right? So I have 2s2, 2p4, right? So 2s2 is already paired. If I go for 2p4, I will have one, two, two. Excuse me. Oh, yeah. So 1, 2, 3, and 4. So you see how many unpaired electrons are there? There are two. What is happening? So there are two unpaired electrons in the valence shell of oxygen. So obviously you see that there are going to be two covalent bonds. I know the structure of oxygen, isn't it? So I have one for one unpaired. Obviously there are going to be two oxygen atoms. Both of them will have two unpaired electrons, and both these electrons will get paired, and I form two covalent bonds. So what I understand is, as many number of unpaired electrons I have in the molecule, that is the number of covalent bonds which can be formed in the molecule. Very, very simple, isn't it? Right. But again, there are so many cases, right, where this doesn't hold good. Okay. Especially if I go for carbon, I mean, if I go for any compound containing carbon, right, this actually doesn't hold good, right? So how, we'll see, right? Say, for example, if I take CH4 as an example, right? So if I take CH4 as an example, let me look at carbon. Let's see what happens, right? So carbon is having 2s2, 2p2, correct? So again, 2s electrons are paired, so nothing we can do about it. But you can see in 2p2, I have 2 electrons, right? Okay, now according to valence bond theory, tell me carbon can form a maximum of how many bonds?
4.
No. That, I know it can form a maximum of 4, but according to valence bond theory, how many it can form?
Sir, is it 2?
Yes, right? Obviously, I should have told you. The number of unpaired electrons decide how many bonds it can form. Now you can see how many unpaired electrons I have. Basically, I have only 2 unpaired electrons in the valence shell of carbon, right? So obviously, it can form only 2 bonds according to valence bond theory. But obviously, we know in CH4 or any other molecule in carbon, which involves carbon, carbon is going to form 4 bonds, right? Again, this is a problem with valence bond theory, right? Okay, so to overcome all these things, right? Again, valence bond theory doesn't tell me the structure, it doesn't tell me the magnetic properties, the strength of the bond. Yeah, so even though it little overcomes the problems of say the what is that, less than 8 electrons and more than 8 electrons, but still it has its own problem like this. Okay, fine. So to overcome all this, we are going to go for the next theory, right? So the next theory, actually, again, I'll be able to combine 2 theories and teach you. So I'm going to combine the theory of hybridization, right? Plus, I can combine this with VSEPR. Okay, so theory of hybridization and VSEPR can be combined together and studied. I know what is the full form of VSEPR: valence shell electron repulsion theory. Okay, fine. So we'll see what theory of hybridization says. But before that, like actually, we'll just revise a few things, people. Okay, fine. So actually, it has to be taught when I taught you covalent bonds the starting, but still no problem. Okay, fine. So tell me, what are the 2 types? Oh, forget about theory of hybridization VCPR for now. I'm just asking normal covalent bonds. Okay, now tell me, there are 2 types of covalent bonds. Can someone tell me what is the 2 types of covalent bonds I can have? Coordinate. Okay, I say then. Okay, fine. I'll have 3 types of covalent bonds. So one of them is coordinate. Okay, so what are the other 2? Yes, that's Sanjana. You are right. Actually, that's also a type of coordinate bond. Sorry, covalent bond. Polar, non-polar, no, that's not what I'm talking about. Okay, let me tell you, it's something owing to overlaps of orbitals. Correct, sigma and pi. That's what I'm expecting, right? Fine. So yes, so there are going to be 3 types of covalent bonds. So as mentioned by Sanjana and Aditi, so the 3 types are going to be sigma, pi, and coordinate bonds, right? So we'll speak about them for a little while, right? So for we know what is sigma bond, right? So again, a coordinate bond is a little different. We'll speak about it separately. But when I speak about your sigma and pi bonds, right, it's all about how the overlap of orbitals are happening, right? How the valence orbitals, right, are involving in overlapping, right? Okay, so yes, we'll just have a discussion quickly for this. Yes, can someone tell me what is the difference between the overlap case for sigma and pi?
Sir, head-on and lateral overlap.
Good, right? So I think let me draw a simple diagram so that you'll be able to understand, right? So when I have a sigma bond, hey, this is not coming under theory of hybridization. This should have been thought before, but still, right? So when I have a sigma bond, when I say, right, so as she told, I'm going to have head-on collision or head-on overlap, right? So if I have 2 two s orbitals will come together and share their electrons like this, right? So you can see, obviously, there is no other way when it comes to s orbitals. There is no other way other than to go for head-on overlap. There is no other way, right? But if I have a p orbital, yes, right? But even if one of the orbital is s, right, it is impossible for me to go for either any other type of overlap other than head-on overlap, right? So I have, so this is my s overlap, right? Now next thing can be an s and a p orbital. Bear my diagram, people, right? So you can say this is an s, this is my p orbital, so this is my sp overlap, and I can even have pp overlap, something like this. Again, head-on collision, right? Okay, so this is my pp overlap. So you can see all of them are going head-on with each other, right? So that is about my sigma bonds. So when I want to go for pi bonds, so I say, so this is my head-on overlap. Like you have to remember, this is head-on collision or head-on overlap. So when for pi, it is going to be lateral overlap, right? So what is going to happen here? Say if I have, now for s, it's impossible. So what are the types of pi bonds I can have? I can have p pi, I can have p pi, d pi, or I can have d pi, d pi. Okay. So d pi and d pi, right? So you can see there's no way that s orbitals are going to get involved here. Anyway, so let me so p pi, d pi, d pi, d pi are little not so important, right? But p pi, we'll see what happens. Okay. So basically, the overlap is going to happen like this, right? So if I mark the these things, right? Okay. So this is how the overlap is going to happen. Say this is going to come like this, and this is going to come like this, right? So if I want to properly tell you how exactly it happens, so something like this, right? So you can see how the overlap is happening, right? So it is not going to be a head-on collision, it is going to be a lateral overlap like this. So this is what is called as your pi bond, right? Okay. So obviously you know how to find the number of pi bonds and sigma bonds in the molecule, right? So the first ever bond which forms between the two elements is always a sigma bond, right? The first ever bond which forms between any two elements will always be a sigma bond. And after that, if you form the second or third or fourth, I mean, fourth is not possible. So if a maximum number of bonds between two elements is three, maximum between between two elements A and B. Maximum I can have only three bonds. Fourth bond is not possible. I can have a fourth bond between, say, this side and this side, but between these two, it is impossible for us to what to say, to make more than three bonds, right? So again, if you look at what is the number of sigma bonds and pi bonds here, obviously I told you the first ever bond is going to be formed as sigma, so there is one sigma, and whatever the extra bonds you form are pi, so you have two pi bonds. One sigma bond and two pi bonds will be existing in a triple bond. This one all we already know, so that's why this just a revision for you. Okay, fine. So I think now we have this thing. Now we can go for theory of hybridization. Okay. One more thing. Now, with this itself, like by looking at what are the orbitals involving, not only in sigma and pi, right? I mean, not only in sigma, but both in sigma and pi. By looking at what are the orbitals involving in the overlap, right? Actually, I'll be able to tell the strength of the bond. Okay. Now, please understand, people, SS overlap is, see, how, like, if I say strength, it is all about the extent of overlap. How much good overlap, how much is the extent of overlap is what is the question, right? So more and more is the extent of overlap, more and more they are closer, right? More and more is going to be the strength of bond, right? So obviously from this discussion, you can understand if I'm going to involve an S orbital, right? Since it's spherical in shape, the overlap is going to be a very, very good overlap, right? I would say the extent of overlap is going to be really good, right? So I would say whenever you have SS overlap, that is going to be a stronger bond than when I have SP overlap, and obviously it is going to be stronger than a PP overlap. Is that cool? And generally, a sigma bond is stronger than a pi bond. Again, the obvious reasons are going to be the extent of overlap. So you can see if it is going to be a head-on overlap, the extent of overlap is going to be really good than in a pi bond where I'm going to have a lateral overlap, right? So yeah, so these are all the things you have to know about sigma and pi bonds. So I think we should have a discussion about coordinate bond also, right? So we'll just have a very small discussion about that, right? So coordinate bond, people, is a special type of covalent bond, right? You already know this. I'm just going to give you one example for this, right? So the best example, the simplest of all example I can take is your carbon monoxide, right? And obviously, is your coordination compounds chapter over for you people in your school?
Yes, sir.
Oh, it's over, right? So obviously, you know, obviously there's so much about coordinate bonds then. Anyways, right? So I'll just give you this small example, right? So carbon is having 4 valence electrons, and oxygen is going to have 6 valence electrons. So this oxygen atom requires just 2 more electrons to satisfy its octet, right? Now, generally, what we see is, say, one element gives 2 electrons. The other element also gives only 2 electrons. That's how it forms. That's how a covalent bond is formed. But in this case, say carbon is giving 2 electrons. So if it is going to take only 2 more electrons, I have 4 electrons already in carbon. And if it is going to take only 2 electrons, I'm going to have only 6 electrons in the valence shell of carbon. And that is unstable. We know that, right? So what is going to happen is, yes, it's going to take these 2 electrons, but that's not the end of it. This lone pair, which I have here, is going to get donated to this carbon, right? So making sure that it is going to have 8 valence electron. And this particular scenario which we have here is what is called as your coordinate bond. And how do we represent it? It's very simple. I have 2 normal covalent bonds, and there is going to be a coordinate bond. And how do you represent it? You are going to put an arrow mark. And how is the arrow mark pointed? It is going to point basically from oxygen to carbon, basically, which is donating electron to what? So it's going to be like this. So if you see the arrow mark, it indicates that there is going to be a coordinate bond in a molecule, in this molecule, right? So coordinate bond is basically a normal covalent bond. 1 electron comes from each atom. In a coordinate bond, 2 electrons come from 1 single atom. That's the basic difference between a normal covalent bond and a coordinate bond. Is that okay? Right. So obviously, for a coordinate bond to be formed, I should have an empty orbital in the carbon, right? Empty orbital, just like how you have resonance or hyperconjugation or whatever it is, where you see that the shared pair of electrons is donated to that, right? So obviously, like this, for a coordinate bond to be formed, not only in this case, for any case for that matter, I should have an empty orbital present in the element or atom. Only then it's possible. Is that cool? Right? So yeah, we discussed all the 3 types of covalent bonds, which we have: sigma, pi, and coordinate. Is that cool? Right? Fine. Now actually we can go for your theory of hybridization. So what is the time? 15 more minutes. Cool. So let me mark, start a page. Right. Right. Yeah. Right. So okay. Actually, I have to write it again. Theory of hybridization plus your VSCPR. Right. Cool. So I said we'll be speaking them. We'll be talking about them together. Right. So anyways, we have to understand them individually together so that we'll be able to just put them together and understand what to say. Theory of hybridization basically explains how a covalent bond is formed, and VSCPR actually talks about the structure of the molecule. So if I put them together, so I can actually understand both the things in the mix of how a covalent bond is formed and accordingly how the shape or the structure of the molecule will be. Anyways, right. So when I go for theory of hybridization, people, right? So till now, whatever you have seen in your valence bond theory or your Lewis theory, right? So you were talking only in terms of atomic orbitals, pure atomic orbitals, say s orbital, p orbital, d orbital, something like that, right? So from now on, we are not going to speak in that way, right? So we are going to speak in terms of something called as hybridized orbitals. We already know this, right? So we are going to speak in terms of something called as hybridized orbital, right? So next question is, what are these hybridized orbitals? So basically, these hybridized orbitals are formed when two or more atomic orbitals, pure atomic orbitals, come together, isn't it? Now, it's not like any atomic orbital, any two atomic orbitals can come together. The only condition is that the atomic orbitals which come together to form the hybridized orbital should be of almost similar energy. In the sense, say I can have 2s and 2p combining. So you can see almost they have same energy. Or say I can have 3s, 3p and 3d combining, something like this. They should have almost appreciably same energy. Only then they'll be able to undergo hybridization, right? Okay. Now, next thing what you have to understand is the number of hybridized orbital. Right? The number of hybridized orbital formed should be equal to the number of atomic orbitals combining. In the sense, if I have two atomic orbitals combining, I should form two hybridized orbitals. Say, if I have three atomic orbitals combining, I should have three hybridized orbitals to be formed. Same goes with 4, 4, 5, 5, 6, 6, 7, 7, so on and so forth. Right? Fine. So we already know what are all the different types of hybridized orbitals I can have. So let me just go for it. If I have one s and one p orbital combining, so you can see that there are two atomic orbitals combining. So I'm going to form two numbers of sp hybridized orbital, right? Same way, if I have s and two p orbitals combining, that is going to end up with three numbers, isn't it? One s orbital, two p orbital, three numbers of sp2 hybridized orbital, and obviously I can, if I have s plus 3p orbitals combining, so I can have four numbers of sp3 hybridized orbital, and other things we know I have sp3d and I have sp3d2, and very rarely you can have sp3d3 also, right? So these are all the different, we already know this, but still, these are all the different types of hybridized orbitals we can have in the theory of hybridization, right? Okay, so two things you have to understand: the orbitals involving, the atomic orbitals involving in the hybridization should be of same energy, and the second thing is the number of hybridized orbitals should be equal to the number of pure atomic orbitals combining to form the hybridized orbital. Is that okay? Right? Cool. Now I'm going to give you a trick, right? Let's see, there are so much information, so much inside details you will be able to get when I'm actually seeing in depth of how these hybrid orbitals are formed, and I will take so many examples, but none of it are going to get asked for you. Say, for example, I will be able to predict how many pi bonds are there in the molecule. I'll be able to predict how many coordinate bonds are there in the molecule. All this can be predicted with the help of theory of hybridization, but none of them are important for your level, right? So what is important is, what is the hybridization? Just by looking at the molecule, right? Just by looking at the molecule, how will you decide what will be the hybridization? Okay, so for that, I'm going to give you a trick, right? Let me add a page, right? So we are going to see how do we predict exactly by not even spending 10 seconds to determine what is the hybridization. Okay, now before we move on to this, people, right? So remember, hybridization, we are going to talk in terms, we are going to talk about hybridization only for the central atom. Only for the central atom. I hope you know, if you understand what is central atom. If I have H2O, oxygen is my central atom. If I have say HCN, okay, now this is a tricky thing, right? When I have HCN, what's happening to my pen? Is everything okay? Yeah, cool. So when I have HCN, people, right? So there'll be a confusion, right? Which to put as the central element or central atom, right? So when I say CA is not a chartered accountants, right? CA is central atom, right? So what I was asking, so yeah, if you have HCN molecule or something, some molecules like this where there is a confusion, right? How do you decide which is the central element? the answer to that question is you are going to take the element which is having least ionization energy, right? So the out of these three, which are not only in the molecule, whichever is going to have the least ionization energy, right, will be the one which is going to have, which is going to be the central atom, right? So in this case, carbon is the one which is going to have the least ionization energy. So that is the one which is going to have that is going to be the central atom. Anyways, so what I'm trying to tell you is we have to speak in terms of hybridization only and only for the central atom, right? So the bonding atoms doesn't matter at all. Again, I repeat, we have to talk about hybridization only for the central atom. The bonding atoms have no role to play. I mean, they have obviously role to play in the sense we are not going to talk about hybridization for the bonding atoms. That's what I'm trying to tell you. Okay, so this being understood, now I'll give you the trick, right? Okay, so there is going to be one number which is going to help me find out the hybridization. So that number is what is called as your steric number. Sn is steric number. So that is equal to, right, number of atoms bonded to the central atom plus, this is one of the component, number of atoms bonded to the central atom plus number of lone pairs in the central atom, right? So you can see we are speaking only for central atoms, right? So steric number is equal to number of atoms bonded to the central atom plus the number of lone pairs in the central atom. Very, very simple, right? So let me give you an example for this, right? Let me take a very simple example. I have CO2 molecule, right? So in CO2 molecule, obviously I know carbon is the central atom. Okay, right. Now, looking at the first component of the steric number, so we have to see how many atoms are attached to the central atom. How many here? Can you tell me?
2.
Yes, 2, isn't it? There are 2 oxygen atoms attached, right? So the steric number for this molecule will become 2 plus there is one more component, that is my number of lone pairs on the central atom or in the central atom. What is that? What is the number? Is there any lone pair on carbon here?
No, sir.
No, right? 0. So obviously you can see that the steric number is 0. Sorry, steric number is 2. Now with this number, how will you predict the hybridization? So please understand, it is actually going to talk about the number of hybridized orbitals are formed, and obviously that is going to be equal to the number of atomic orbitals combining, right? So if you see that the steric number is 2, that means 2 atomic orbitals are combining. And I know there is only one possibility for that when I have one s and one p orbital combining. So obviously for carbon, in this case, it is going to be sp hybridized, right? So obviously if you find steric number 3, I'm going to have sp2. If you find a steric number as 5, it is going to be sp3d. So one s orbital, 3 p orbitals, and one d orbital, totally 5. So if you find a steric number as 5, I'm going to have what is that? sp3d hybridization. Okay, so we'll take more examples. Like you are going to tell me. Obviously, quickly, we'll go for this. Okay, fine. Let me have ammonia. Right. So ammonia, quickly go for it and tell me what is the steric number and what is the hybridization. So guys, you have to find out, see if there are any lone pairs, you must know how to find out the number of lone pairs, right? So for that, it's better to go for the Lewis-Dot structure. But again, now I think you have crossed all those points. You don't have to draw the Lewis-Dot structure to find out the number of lone pairs. You can directly find it out. But if you're still finding it difficult, please do not be lazy. Draw the Lewis-Dot structure and then try to find out the number of lone pairs.
Sir, one lone pair.
Yeah, one lone pair. Good, right? So what is the steric number?
4.
4, right? So you can see that the number of atoms bonded to the central atom is 3, and the number of lone pairs on nitrogen is 1, so making it 4. So what is the hybridization?
sp3.
Yes, sp3. Okay, now let me little elevate your levels. So I have XeOF4. Okay, I have XeOF4. Tell me, obviously the central element is going to be xenon here, right? Tell me the hybridization, sorry, tell me the steric number and the hybridization. And remember people, whenever you see oxygen, 99% of cases, you are going to have a double bond with that particular element. I mean, oxygen and that particular element is going to have a double bond. Please remember that.
Sir, sp3d2.
sp3d2, we'll check it, right? So if you look at it, I have a double bond oxygen and all single bonds fluorine. And basically you see that xenon has 8 valence electron, noble gas element, right? So how many of them are involving in bonding? 1, 2, 3, 4, 5, 6, right? So 6 electrons are involving in bonding. So how many lone pairs, sorry, how many electrons are left out is 2. So I have only 1 lone pair. No issues. Again, I repeat. So you have how many bonds you see? 1, 2, 3, 4, 5, 6. Right? So 6 electrons are involving in bonding. There are 2 electrons left out. That means obviously I have 1 lone pair to be present. So when I go for the steric number, you can see that how many atoms are attached? 1 oxygen atom, 4 fluorine atoms, totally making it 5. And how many lone pairs? Lone pair is 1, making it 6. So obviously I'm going to have sp3 1 2 3 4 sp3 2. Yes, your answer is correct now. So it is going to be sp3d2. Yes. So like this, just by looking at the molecule, you can predict what will be the hybridization. Okay, right? Fine. I think you can take your breaks, people. Right? I'll be meeting you at say it's 10:57, but still I'll meet you by 11:15. No issues at all. Right? So we'll come back and join us. I mean, we'll join together at 11:15. Right? So you can go take your breaks. You can go do whatever you want and come back by 11:15. Right? Cool, people. I'll meet you in another 15 minutes. Let me mute myself. Okay, hope everyone is there. Are you back, people?
Yes, sir.
Okay, cool. So we continue.
Yes, sir.
Right. So yeah, so we have seen what is the shortcut to find what is the hybridization of any molecule for that matter, right? So yes, now what we'll do is we'll go for VSCPR. We'll start my page, right? Cool, right? So when I go for VSCPR, people, right? Now I told you, what is that theory of hybridization talks about how a covalent bond is formed, and VSCPR is the one which is going to predict the structure or say the shape and geometry of the molecule, shape and geometry. Okay, so there's a small difference between what is the, I mean, there's a small difference between shape and geometry. It's not exactly same. Sometimes yes, they can be same, but whenever you have lone pairs on the central atom, the geometry and the shape will be different. Okay, fine. What we'll do is we'll make a table now, or let me put it this way. First, we'll take down the statement for VSCPR. Please take down the statement, people. The statement for VSCPR, right? That goes like this. The shape or geometry of the molecule, the shape or geometry of the molecule should be in such a way, that the repulsions between electrons, such that the repulsion between electrons is minimum, such that the repulsion between the electrons is minimum. As simple as that, right? So obviously the shape or geometry is going to be based on the electronic repulsions, right? So it's not all type of electrons you're going to take into the picture. Obviously you're going to take only two types of electrons, that is my bond pairs BP and the lone pairs, right? Okay, so obviously you can have different type of interactions. That means in the sense different type of what to say, different type of repulsions existing between this bond pairs and lone pairs, right? So there can be only three types of repulsion. One is what is my bond pair repulsion. The other one is the repulsion between bond pair and lone pair, and the last it was only going to be between lone pair and the lone pair, right? So obviously if you can think about it, bond pair is already stabilized, right? They are going to be little inside, so the repulsions between them is going to be little less. But when I compare with lone pair repulsion, that is going to be really outside, right? So obviously the amount of repulsion, if you check, the lone pair repulsions are greater than the bond pair lone pair repulsions, and the least repulsions are going to be for bond pairs, right? So based on this only you have to decide what is going to be the shape, right? Okay, so for example, when I take steric number 2, right? So obviously when you see that the steric number is 2, I'm going to have sp hybridization. Okay, so now I'll take an example. Say like the type of molecules I can have is like AB2 type of molecule, right? So in this case, you see that there are no lone pairs on the central atom, right? So there are only going to be bond pair repulsions. So now I have to make sure that the bond pair repulsions are minimum. Now, how can I make sure that the bond pair repulsions are minimum? Is by making sure that the distance between the bond pair is maximum, right? I have to make sure that the electrons are as much as far away from each other, so that the repulsions are minimum, right? And the only way I'll be able to put that is when I put the structure like this, right? When you see that the bond pair, or is it the bond angle for this, if it's 180 degrees, right? That is the maximum distance I can have. Say if I'm gonna little put it like this or little put it like this, obviously the repulsions are going to be maximum. Some repulsions are going to be there. The minimum repulsions I can see is that when I put the molecule in this way, that is this particular shape or geometry is what is called as your linear shape or linear geometry, right? So like this, we'll be able to predict what will be the shape of the geometry of the molecule. Okay, so what we'll do now is we'll make a table, right? So that table is going to be really helpful for you. Let me add a page, right? So in this table, what are we going to do is we are going to put first the steric numbers in one, and then I'm going to have steric number, the type of molecule, right? Next, I'm going to have steric number, type, and what else? Hybridization is obviously done with steric number. Type is we'll see. Okay, then say the shape or first the geometry, right? Geometry, right? And I'm going to have the shape. Okay, and the last one is going to be my bond angle. Right? So these are all the things which are there in the table. Okay, fine. So the least steric number we can have is 2. Okay, so the first type, and in steric number 2, there is only one type, and the type of molecule can be AB2. See, AB2, A is the central atom, B is the bonding atom. Okay, so just now we saw, right, the geometry and the shape. Okay, let me tell you what is the difference between geometry and shape. Okay, so I told you geometry and shape are going to be same when I have no lone pairs. Okay, but when I have the lone pair, the geometry and shape are going to be different, right? How do I put it in better words? Is that shape is the consequence of change in geometry because of the lone pair. Again, I repeat, shape is the consequence of having the lone pair, right? Shape is the consequence of having lone pair, and obviously that is going to change the geometry. Okay, now in this case, you don't have to worry about it. When I have AB2 type of molecule, that is when I have steric number 2, both the geometry and your shape are going to be same. That is linear. And just now we saw the bond angle is 180 degrees. Okay. And people, I will not be able to fill the table completely. Like I will be giving you example. I'll be giving you different types, different shapes, different bond angles, and you are going to fill the table by yourself. Okay, fine. So next, when I go for steric number 3, right, in steric number 2, there is no other possibility. You can ask me, sir, I can even have something like ABL. ABLL represents the lone pair. Okay, B represents the bonding atom, and A represents the central atom, right? So there is no such molecule like this. Okay, you don't have to worry about it. There is no such molecule which is going to have ABL type of, that is when I have steric number 2. One bond pair, one lone pair. No, it is never going to be like that. Okay, so when I go for steric number 3, let me take this thing first. When I don't have lone pair, and I have AB3 type of molecules, right? So obviously, again, I have to make sure that the distance between them is maximum. That is, the distance between the bond pairs is maximum. And the only way I can do this is by putting them in this way, right? So you can see that the bond angle here is going to be 120 degrees, because total angle is 360. 360 divided by 3 is going to become 120 degree. So this is the most stable structure, right? So the shape, you can see, if I draw a triangle, it is all these molecules, all these bonding atoms are going to be in the same plane as the plane of my laptop or the screen, right? So the shape is going to be called as triangular, or sorry, not triangular, trigonal planar, right? Again, as I told you, whenever there are no lone pairs, I'm going to have the same shape and geometry, and here the bond angle you see is 120 degrees. Okay, now next, same steric number 3, but if I can have AB2L, that is 2 bond pairs and 1 lone pair. Okay, now any examples for this type of, okay, first of all, now tell me, is there any example for AB3 which you can think of? The actual molecule, any examples? Let me look at the
BF3.
sorry. Yes, BF3. BF3 is a very good example, right? So BF3, you can see there are no lone pairs on boron, but there are 3 bonding atoms. So obviously BF3, the shape of them is going to be trigonal planar. The geometry and the shape is going to be trigonal planar. Is it okay? Right? Cool. So now I'm going to take this AB2L. Any examples for this? You can think of any example for AB2L? Sorry?
NH3.
NH3. NH3, what do you have? In NH3, how many bonding? I have a lone pair, good. But what about the number of bonding atoms? It's 3, right? So that comes from the type of AB3L. No, this is not thing. That means the steric number itself is different. Steric number is 4 here. Is it not? Okay. So the example can be, I think it should be NO2. Is it possible? We'll try it. We'll try to check the structure. So guys, I don't have space here, but as and when I complete a particular type of the molecule, you are going to fill the table, because that table is going to be very, very helpful for you. Okay, fine. Let me make a page. Or right. So in NO2, we'll see what happens. We already saw this, but we'll try to do this. So I have will it work? NO2, or if I take NO2 minus, will it work? Yeah, NO2 minus will work, people, right? So I'm gonna take NO2 minus. Okay, and see, whenever you have this kind of problems, whenever you have charges coming into the picture, okay, so remember that the negative, if you have a negative charge should go to the bonding atoms, right? Negative charge should go to the bonding atom, and the positive charge should go to the central atom. This is one way of looking at it. Or the other way of looking at it would be a negative charge should go to the more electronegative element, and the positive charge should go to less electronegative element. Okay, so both of them will work, right, in most of the cases, but sometimes you can have a discrepancy in this. But anyways, so for now, what you have to understand is oxygen is the one which is going to have the lone pair. Is that cool? Right? So one of the oxygen atom is going to be O minus, and the other oxygen atom is going to be neutral. That's what you need to understand. Okay, so let me make this oxygen atom neutral. So it has 6 valence electrons, and the other oxygen atom is going to be O minus, that is going to have 7 valence electrons, because 1 electron is extra added because of the negative charge, right? Okay, so there is 1 electron, 2, 2, and 2. So it is 7. Right, let me rewrite this little thing like this. Okay, now if you look at this, right, so this oxygen atom requires 2 electrons to satisfy its octet, done. And this oxygen atom requires only 1 electron to satisfy its octet, done. And obviously all the shared pair of electron the nitrogen is going to take. So what do you see here? Obviously there are going to be the structure, if you look at it, minus, and you see there's a lone pair. You can see that is here. There's a lone pair on nitrogen. Okay, so NO2 minus is a very, very good example for AB2L type of molecule. So 2 bonding atoms and 1 lone pair. Okay, now what is going to happen to the shape and geometry? See, remember, irrespective of, let me put it this way. For a particular steric number, for a particular hybridization, the geometry is constant. For example, if you have steric number 3, so you can have 2 possibilities. Just now I told you AB2 and AB3 and AB2L, right? So both of them, the geometry is going to be trigonal planar, right? The geometry I'm talking about, these are the geometries, right? So the geometries are going to be same for both of them, but the shape I told you will be different when I have lone pair, right? Now obviously what you have to understand is you are going to have a new type of interaction here. The interactions are going to be between the lone pair and the bond pairs, isn't it? So obviously the molecule cannot be linear. Yeah, so if this lone pair is not here, right, if this lone pair is not here, obviously you can tell that it is going to be linear. But since this lone pair is there, these two are gonna come down like this. So the distance between the lone pair and the bond pair is increasing. Okay, so if I want to properly draw the structure, this is how I properly draw the structure. Okay, so making sure the distance between the bond pair and the lone pair is maximum, right? So obviously you can see you can look at this and tell me what will be the shape. The shape is going to be bent shaped, or it is also called as V-shaped molecule. Yeah, so bent shaped or V-shaped. Now please fill the table. Just go for steric number 3. The type of the molecule is AB2L. The geometry is still same, trigonal planar, right? But the shape is going to be bent shaped. And the bond angle will not be able to predict exactly because it is going to depend on the type of atoms present. So just put a dash for bond angle. Is that cool? Right? Hope you have filled the table. Again, I repeat, AB3L, steric number 3, AB3L type. Geometry is still trigonal planar, but the shape is bent shaped or V shaped. Just put a dash for your bond angle. Is that cool? Right? Fine. So that's about AB3L. So let me make the page. Next, we'll go for steric number 4. These are the only two types present in steric number 3, people.
Sir, that's
right?
AB2L, no, sir.
Sorry. Yeah, it's AB2L. I'm really sorry. Yes, AB2L, and the shape is bent. Yes, correct. AB2L. Right. Cool. So now we'll go for steric number 4. Right. Steric number 4. The first type I'm gonna take is AB4 without a lone pair. All 4 bonding atoms. Yes. So any molecule you can think of. So many are there.
CH4.
Yes, the simplest of all examples can be CH4, right? Okay, so we already know what is going to be the bond angle or what is going to be the shape. What is the shape, people?
Tetragon. Tetrahedral.
Yeah, it is tetrahedral, right? Okay, so how do you write the shape? Like, let me tell you that. So I have A. So you are going to have 2 bonding atoms in the same plane, right? And there are going to be 2 other bonding atoms which are going to come. One is going to come out of the plane and the other one is going to go inside the plane. So for that, we'll be using your wedge and dash structures, right? Say this, if I put a dash structure, it represents that the bond is going inside the plane, right? Inside the board of the screen, right? And there is going to be a wedge which says the bond is coming towards you, right? So there is a bonding atom like this. So this is the shape. This shape is what is your tetrahedral shape, right? And obviously, I know what is the bond angle. Bond angle is 109.5 degrees. Okay, so 109.5 degrees is the bond angle. I'm talking about this bond angle. This, something like that, right? So that's my bond angle. Okay, very simple. Okay. Fine. So the next type we'll take is AB3L. That is, I'm going to have 3 bonding atoms on 1 lone pair. And the previous example that you gave me for that one is going to help here. And the example is going to be NH3. Right? So again, the geometry for this is going to be still tetrahedral, but the shape will be different because I'm going to have a lone pair on nitrogen, right? So how the shape is going to look, this is how the shape is going to look. Right? So there is going to be a lone pair, right? So this particular shape is what is called as your pyramidal shape. You can see, right? It's like a pyramid, is it not? So this shape is what is called as your pyramidal shape, right? Cool. So again, fill the tables, people. For steric number 4, I have 2 types. First one is AB4. The geometry and the shape is tetrahedral. The bond angle is 109.5 degrees. And the second one is going to be AB3L, right? The shape is pyramidal, but the geometry is still tetrahedral. Geometry is tetrahedral. Shape is pyramidal. Again, I'll not be able to predict what will be the bond angle. I can just say that it will be less than 109.5 degrees. For sure, that I'll be able to say, right? It will be less than 109. So if you look at the actual bond angle will be around 107 degrees. Right? Okay, so anyways, so now this we have filled. There's one more type in this. The next type is AB2L2. Right? Oh, guys, please understand, for all of this, the hybridization is sp3. Please don't forget that. Anyways, so the next type in steric number 4 is AB2L2. Any examples for this?
H2O.
Water.
Good. Yes, very good. So H2O is a very good example. You can see that I'm going to have 2 bonding atoms and oxygen has 2 lone pairs. So 2 bonding atoms, 2 lone pairs. So you see that okay, if I draw it properly, you have A, B, B. Now there is going to be 2 lone pairs, right? So obviously you can see there is lone pair interactions also. This is the first molecule you see there is going to be a lone pair interaction. So definitely the lone pairs will try to move far away from each other. This means this will move this side, this will move this side. But if they move this side, obviously the interactions between the lone pair and bond pair is going to increase. So the molecule is going to be really very constricted, right? So again, if you just forget the lone pairs are there, if you just forget that lone pairs are not there, you can see that this shape is again going to be bent shaped. Okay, and the bond angle, if you check last time when I had AB3L, the bond angle was 105. Now I have lone pair interactions also, so the bond angle in this case will be around 105 degrees. Okay, so the bond angle will be still lesser in water, right? So anyways, you don't have to write the bond angle, just write AB2L2. The geometry is still tetrahedral, right? And the shape is going to be bent shaped, and the bond angle, you don't have to write anything, right? Just put a dash, right? So that is about steric number 4. Cool, right? So we'll move on to the next steric number. These 3 are the types in steric number 4. Done? Okay. Okay, next, steric number 5, right? So steric number 5, first I'll take AB5 without any lone pair. Okay, any examples?
PCl5.
Yes, PCl5 is a very good example, right? So you can, now I'm going to look at the shape, right? I mean, geometry and the shape are both going to be same here. So this is how the shape is going to look, right? So here, this molecule is little complicated when compared to other molecules, like other types of molecules, right? So here, this is how the shape is going to look, right? So you have 3 bonds in the same plane. Okay, you have 3 bonding atoms in the same plane. Okay, right? Now, other 2 bonds, basically, okay, and other 2 bonds are going to be like this. Okay, so if you look at the shape, this is my trigonal. If these 2 are not there, I would say this is trigonal planar, right? Now what you have is these 2 are also there, so the shape or geometry here is going to be called as trigonal bipyramidal. Now you can see, right? I think from the name itself you can understand why the name is such, right? So you have a trigonal shape, right? And obviously you have one pyramid at the top, another pyramid at the bottom. So something like this, right? So you can see a trigonal shape is there, and there are going to be 2 pyramids, one at the top and one at the bottom. Okay. Now, obviously, I know what is the hybridization here. Hybridization is sp3d. Okay. Now, see, you have 5. Okay, if I draw the structures again. Right. So you have the bonds in the trigonal plane, right? And obviously you have 2 other bonds in the, okay, so I'll tell you what is the axial plane, I'll call it, right? So there are going to be 2 types of bonds here. Okay, so one is what is called as your equatorial bonds, right? Equatorial bonds. The other one is what is called as your axial bonds. So axial bonds are these 2, right? And the equatorial bonds are these 3, right? So you have 3 equatorial bonds and 2 axial bonds. Now, why are we calling it different names? Is because the bond lengths, the bond angles, everything is going to be different for equatorial and axial bond. Please understand that. Okay. Now, how will I try to visualize this? Is that I will be able to split this sp3 dehybridization as sp2 plus pd. Okay, sp2 plus pd. So sp2, obviously I'm going to have the trigonal shape, and the pd, I assume that it is like sp, right? So if I have pd, it is going to be linear, is it not? So this space, this shape or geometry, whatever I have, is going to be a combination of trigonal as well as linear, and that ends up with your trigonal bipyramidal shape. Is that cool? Right. Now, the next question is, oh, I told you that the bond lengths are going to be different and the bond angles are also going to be different, isn't it? Now, you can easily check it. The bond angle, if you look at here, for axial bonds, the bond angle is 90 degrees, right? And for equatorial bonds, I already know what is the bond angle. For equatorial bond, it is going to be 120 degree. You know, you can actually bring this from the previous discussion itself, right? For trigonal planar, obviously I saw the bond angle was 120, and for linear it was 180. But for you see, this bond angle is 180, obviously. But if I check this bond angle, that bond angle will be 90 degrees only. Is that cool? Okay, so we have two different bond angles here, 120 for equatorial and 90 for axial. That is done. And the next question is, what about the bond lengths? Right? Now, please understand, now we already know that when I have an s orbital present, right? When I have an s orbital present, the bond is going to be really strong. Is it not? Right? So obviously, when the strength of the bond increases, that means what? The atoms are very close to each other, right? So a stronger bond in general will have shorter bond length, and a weaker bond in general will have a longer bond length, right? So now talking about the strength of the bond, talking about the strength, right? If you talk about the strength of the bond, equatorial bonds are stronger than the axial bonds, right? So obviously, if I talk about the bond lengths, you can easily predict it. I can say that the axial bonds are longer than the equatorial bonds because equatorial bonds are stronger, axial bonds are weaker. So this we need to know. There are going to be two different bond lengths, two different bond angles. Equatorial bonds are stronger, so their bonds are shorter, and the equatorial bonds are going to have a bond angle of 120 degrees, and axial bonds are going to have a bond angle of 90 degrees. Is that cool? Right? So again, you can now go to the table and finish it. Support steric number 5, AB5 type of molecule, right? So you write the shape and geometry both as trigonal bipyramidal, right? And you write two bond angles, right? Equatorial equal to 120, axial is equal to 90 degrees. So that's how you're going to write the bond angles, right? Okay, right. Now, if I want a little complicated, so if I have TCl5, there's no problem. All the axial and equatorial bonds are going to be chlorine atoms, no issues, right? But if I have a molecule like this, I have TCl3F2, something like this. If I have, now there'll be a confusion, right? Where should I put the fluorine atoms, whether in axial or equatorial, and where should I put the chlorine atom, whether in axial or equatorial? Okay, so for that we have a rule. We have a scientist who worked on this, and he told that this is how it should be, right? So that rule is what is called as your bent rule, or I would say Bent is the name. Bent is the name of the scientist, not the shape, right? So Bent's rule. Okay, so please check down the statement for Bent's rule. Actually, there are two statements. If you have a say what is that, an unsymmetric molecule like this, there is one rule. And when you have a lone pair present in this trigonal bipyramidal geometry, again there's a rule for that. Both of them will take it at the same thing, right? So take down Bent's rule. Okay, the statement goes like this. In case of an unsymmetric molecule in trigonal bipyramidal geometry, you can write trigonal bipyramidal as TBP. TBP is a short form, trigonal bipyramidal, right? So in case of an unsymmetrical molecule with TBP geometry, the more electronegative element, should be placed in axial position. Should be placed in axial position. Right? I think the statement is self-explanatory. So if we have two different elements like this chlorine and fluorine, the one which is more electronegative should be put in the axial position. That's what it says, right? So I think you will be able to easily predict the shape now, the geometry now, or whatever it is, right? So if I have PCl3 F2, right? This is how it's going to look. So phosphorus, right? So as I told you, the more electronegative element should be placed in the axial position. So the more electronegative element is obviously fluorine. The two fluorine atoms will come in the axial position, and the three chlorine atoms will be in the equatorial position. So a lot of times I've seen questions coming from these people. Be very careful, right? The more electronegative element, this is only for trigonal bipyramidal geometry, for nothing else, right? Obviously, only in that I have two different types of bonds. Anyways, so the more electronegative element in the axial position. This is the geometry of the molecule. Okay, right? So, okay, say I'll give you one more example. If I have OSF4, okay, OSF4 is a molecule, right? So can you just draw it on the paper? What will be the geometry? Anyways, I will draw, and after I draw, you can check it whether it's correct or not. So remember, sulfur is a central atom here. Okay, hope you would have drawn it, right? So sulfur in between. So let me put the bonds. Okay, fine. So you have oxygen and fluorine. Obviously, fluorine is more electronegative. There are 4 fluorine atoms. So the first priority, 2 fluorine atoms will go to the axial position. No doubt about it, right? So you can ask me, sir, I have 2 more fluorine atoms. Where should I put it? There is no other choice for you than to put the 2 fluorine atoms in the equatorial position, because there is no choice, right? And obviously, there is one element, oxygen, missing. And obviously, oxygen is going to have a double bond with sulfur. So this is how it is going to look. Right? How many of you got this right? Anybody got this right? Whatever I draw?
Sir, I forgot to
whatever
put the double one.
Okay, no issues. That is a common mistake. But still, you should have got the other things right, hopefully.
Yes, sir.
Right?
Yes, sir.
Good. Right? Good. So remember, this should you not forget. Whenever you see oxygen, there should be 2 bonds for oxygen. Unless and until oxygen is central atom, you will have okay, Aditya, it's the same problem. Cool, no issues. Right? So whenever you have oxygen atom to be a central atom, then you have 2 single bonds. But whenever you see oxygen atom as a bonding atom, definitely there should be a double bond. Okay, cool, no issues. I think most of you would have got it right. Very good, people. Right? So yeah, that's about AB5 type of molecule. Right? Now next, I can go for the next type of molecule is AB4. AB4L. Again, so the steric number is 5, but in this case, I'm going to have 4 bonding atoms and 1 lone pair. Right? So again, the geometry is going to be trigonal bipyramidal geometry only, but we have to know where should I put the lone pair. Okay. So again, the bend tool, I told you there are two statements, one for this unsymmetrical molecules, the other one is for this lone pair. Okay. Just write bend tool again, and we'll take the statement. Right. So the lone pair should be placed. Okay, the lone pair in a TBP geometry. Lone pair in a TBP geometry should be placed in equatorial position. In an equatorial position. So the more electronegative atom goes to axial position, and the lone pair, if you have any, should go to the equatorial position. So people, if you ask me reasons why is it like this, the reason is that if I put the lone pair in the axial position, the number of lone pair bond pair repulsions are going to be more. Okay, but when I'm going to put the lone pair in the equatorial position, the lone pair bond pair repulsions are lesser. Okay, that's the reason behind it, right? You don't have to so much delve into it. You don't have to worry, right? So putting the lone pair in the equatorial position decreases the repulsion. That's the reason. Okay, right. So fine. So any example for this AB4L? Can anyone think of any examples? Okay, let me look at the chat if there is any. SF4, yes, very good example. Good, Aditi. Good. Yes, SF4 is a very good example. Okay. Oh, I think there was one more, isn't it? 1 second.
Sir, SOCl2.
SOCl2, XeCl4, XOCl2. What did you say, Kanna?
SOCl2.
Oh, SOCl2. SOCl2. How many bonding atoms are there? Only 3 bonding atoms, no? Oxygen,
Oh, yes,
2
sir.
chlorine
Yes, sir.
atoms. Okay. So XeCl4 or XeCl4 doesn't exist, Harini. XeF4 exists. Okay, but XeF4, tell me what is the number of lone pairs, Harini, there? If I have XeF4, what is the number of lone pair on this one? Xenon?
Oh, sir, it's 2. Okay.
Correct. So again, that's not the answer. Good. Anyways, good try. So SF4 is a very good example, and there are xenon compounds which will be of this type. We'll see that. Okay. Cool. So fine. So let me take the first example which is given to me, SF4. Right. So sulfur is going to be at before. Okay, fine. Sulfur is going to be at the equal at the center, and there are I'm doing a mistake, right? So sulfur, and first of all, let me see. Okay, so let me see how is it that sulfur belongs to this category, right? So obviously there are 4 bonding atoms, and sulfur basically has 6 valence electrons. Okay, let me take out the charger. I think that's why it's little buffering. Just a second, just give me a moment. Right. So yeah, so sulfur has 6 valence electrons, and in that 4 are involving in bonding. So there are 2 electrons left out. Obviously, making sure that there is 1 lone pair. Beautiful. Right. So that's my SF4 belongs to AB4L category. Okay. So first, let me draw the axial and equatorial bonds. Now, as I told you, there is 1 lone pair, and this lone pair has to go to this position. That is the equatorial position, and all the other fluorine atoms are there wherever they are. Right? Fine. Now, now the geometry is this, no doubt, but the shape you have to be very careful. Now, what I'm trying to tell you is just forget that this is there, right? Forget that this particular lone pair is there, right? And if you just twist this molecule, right? Let me write it like this, okay? So you have S, F, F, and you had another F, like this, and obviously there was a lone pair here, but anyways, you can forget about it, right? So if you see, this particular shape is in the form of a seesaw. I think I have to turn on my video so that you'll be able to understand. 1 second. Oh, it's ulta. Yo. Okay, let me change it and again change it for you, no issues. Okay, so hope you're able to see my video. So people, what you see here is I have the two fluorine atoms like this. Okay, and you see there are two fluorine atoms like this also. Is it not? So say these two fluorine atoms are going to act as the fulcrum. You know what is the fulcrum? The support, isn't it? And these two fluorine atoms can go like this, right? So that's why we're going to call it as a seesaw. Hope you understand what I'm trying to tell you, isn't it? So you can see from the shape itself. I think if I can show you, oh, 1 second. Nice new setup, sir. Now only you're seeing Srivatsan. Right?
Sir, I was absent for like 4 classes because of exams, sir.
Oh no, this is the second time. Yesterday was the first time actually I'm taking this for you. But for 11 CBSE, yes, it's been almost like 3-4 classes since I'm using this.
Nice,
Okay.
sir.
So anyways, cool. So I hope you understand, right? How is it seesaw? There is something like this. There is something like this, and they can go up and down like this. Okay, cool. So yeah, so that's, I think I have to change my screen again, people. I'm sorry, I have to stop my video. Okay, again, I have to tilt my laptop. So yeah, this is a 360-degree laptop, Dell. I got this in your this thing, Amazon Big Billion Day. Recently only I got it. This was supposed to be some 88,000 laptop, but I got it for around 58,000 rupees. So yeah, it's a good offer, and I took it. Right. So yes, there is a message definitely regarding laptop. Yes, damn, yes, true. Right? Yeah, it was very good offer, and the laptop is pretty good, people. Right? So it has a touch screen, it has 360-degree flip, and yeah, it has this what is the stylus support, right? And I have almost like 8 GB RAM, and I don't know, like you see, I'm not much of a technical guy. I'm really, if you really want to know, right? I don't even have a social media account. I had Facebook account long back, but I deleted my account. If you try to search my name, you will not be getting me. On Instagram, I don't even have an account, right? So I'm not much of this into this computer games or say social media and stuff. WhatsApp also I have just because I need to communicate with people. If not, even I'll not have that also, right? So anyways, so the specs these are like 8 GB RAM, and what else? This is i7 8th generation, I guess, right? So yeah, pretty good laptop. Anyways, so what I was telling, yes, the seesaw. We'll come back to the seesaw, right? So yes, AB4L will have the geometry to be TBP. Just fill the this thing, people, fill the table, right? So you have the geometry to be trigonal bipyramidal geometry, and what is it? The shape is going to be seesaw shape, right? See, you don't have to mug up the shapes, right? If you can remember the bent rule, you can actually come up with the shape. Just have to remember that the lone pair should be placed in the equatorial position. Yeah, so the lone pair should be placed in the equatorial position, and you can just flip the molecule and check. It is definitely going to be seesaw, right? Cool. Yeah. So that's about AB4L. And any other example you can think of? Xenon compounds, yes. So if you can have, I think, XC O2F2, will it work? Oxygen 4 will be gone. Yes, this will work. XCO2F2 will work, right? So if you want, we can just make a page. Oh, there was a chat. What is it? Yes. Good God tired. I don't know what do you mean by that. Still, anyways. So what I was telling is, yeah. So when I have XCO2F2, guys, please bear my handwriting. Okay. So XCO2F2. So xenon. So first, let me check how many lone pairs are there. Say for each oxygen atom, you know that it is going to be a double bond. So 2 electrons are there for 2 oxygens. So 4 electrons are gone here itself for oxygen. And for fluorine, 1 electron each. So 2 electrons here, totally making it 6. And obviously xenon has 8 valence electrons. So 6 minus 8 will become 2. There is 1 lone pair. Again, you see the shape is going to look like this. If I will directly put the seesaw shape, okay. Again, okay. Let me put the trigonal pyramidal geometry, because you see there are both the bend rules are going to come into the picture. That is, you have a lone pair and you have unsymmetrical molecule also. Is it not? So you try it. Okay, I'll give you 30 seconds time. Just draw a geometry. I don't want the shape. Shape will come back. It obviously is going to be seesaw. Just draw the geometry. Right. So hope you have drawn it. So if I mark it, your axial and your equatorial bonds. Okay, so fluorine is more electronegative, so no doubt fluorine has to go to your axial position. And obviously there are two oxygen atoms and both of them are double bonds. So oxygen here, and the lone pair has to go to any one of the equatorial position. So this is how it looks, right? So I think almost all of you should have gotten it correct. Now that we have seen so many things, I'm going to ask you how many of you got it right, because I have the confidence that most of you would have gotten it right. Okay, so this is the geometry of the molecule, right? So if I just flip it and draw the seesaw shape, this is how the seesaw shape will look. Right? So this is, and obviously there'll be a lone pair, but you don't have to represent it. Doesn't matter. So this is how XeO2F2 molecule will look. Is that cool? Right? Fine. So that's about AB2L. Sorry, AB4L. 4 bonding atoms and 1 lone pair. Right? Okay. Now next we'll go. Now still there are molecules here. Let me go for AB3L2. Okay. So again, the steric number is still 5. Right, but you have two lone pairs and 3 bonding atoms. Right, what's the time? Oh, seriously, time just flew away. I don't believe that 45 minutes are over. Okay, cool, fine. So AB3L2. Right, so again we'll try to put the geometry first. So again the bend rule still stays. Now remember there are 3 equatorial positions. So in this case 2 of the equatorial positions are going to get occupied by lone pairs. Right, so you have, right? So you have 3 bonding atoms. So first we didn't put the lone pair. Lone pair is here. I mean, 1 lone pair, 2nd lone pair, and the 3 bonding atoms. There is no other choice. You have to put it in here. Okay, right. So now, right now this is the geometry. Now how will you bring about the shape? Just forget that this is there. The lone pairs are there. Now what do you see here? This is going to be what shape?
T shape.
Yes, right. This is going to be T-shaped molecule, right? So again, if you remember the bend rule, you really don't have to by heart the shapes, right? So remember that you have to put the lone pair in the equatorial position, and after you put it in the geometry, just forget that the lone pairs are there, and you look at the shape. It is going to be T-shaped molecule. Okay. Next question. Example for AB3L2. Maybe there's some chat box. Okay, you gave the explanation. The laptop is God level, sir. Okay, fine, Stewart, sir. Thank you. So yeah, example for AB3L2. Even I'm thinking about it. Right? So I think I can have ClF3. Oh, ClF3. Yes, works. Good. ClF3 works. Wonderful. 3 bonding atoms. Yeah, good, Aditi. Yes, ClF3 works. Right. So let me check how it works. I think I have to make a new page. See, I really have to work on, what is this? The stage conservation. But anyways, there's no papers getting wasted. Still. Okay, add a page. Right. So ClF3. So again, chlorine has 7 valence electrons. Out of that, 3 are involving in bonding. So there are 4 electrons left out. And obviously there are 2 lone pairs. Yes, absolutely works. Right. So ClF3, how will I draw the shape? Cl F, F, and F, and there are going to be 2 lone pairs. Very simple, right? So this is how ClF3 looks. Good, right? So again, go to the table and write AB3L2. Steric number is still 5. The geometry is still trigonal bipyramidal, and the shape is T-shaped, and you don't have to worry about the bond angles. Right? It'll be, I would say, it'll be little close to 90 degrees, but still, it might change depending on the molecule. Right? Okay. So the of the table is filled. That's about AB3L2. Okay. Next, I go for AB2L3. Now I'm just putting it ulta. That is, I have 2 bonding atoms and 3 lone pairs. So I think we'll be able to easily predict what will be the shape. So yeah, so there are 3 equatorial positions. So 3 lone pairs are going to go here, and the bonding atom, one of the bonding atoms, and the other bonding atom. Right. So again, how do you bring over the shape? Just forget that the lone pairs are there. So what shape do you see?
Linear.
Linear. Wonderful, wonderful. So this is my linear shape. And examples. Now this is a tricky example. Now, since that you have completed your P block elements, I think you should be able to give me an answer for this. And if you're not able to give me an example, I'll completely understand because it's a little tricky.
Sir, example for AB2L3, sir.
Yeah, AB2L3. Yes.
ZeF2, sir. Xenon difluoride.
ZeF2. Yes, I think it works. ZeF2. Yes, it works. Wonderful. Yes, that works. Okay. So yeah, XCF2. Right. I mean, whatever. Fine. So XCF2, you can see xenon has 8 valence electrons and 2 are involving in bonding with fluorine, right? So obviously I have 6 electrons left out and 3 lone pairs, right? So obviously the shape is going to be the linear shape. Okay, fine. Now I have another example for you. That is my I3 1 minus, or I can even have say ClF2 1 minus. Okay, now let me ask you this. This ClF3, ClF2 minus, what are these called as in general, people? Hope you have finished your P block. If you have finished your P block, you'll be able to answer this question. I3 minus is not under that category, right? But ClF3 and ClF2 minus, ClF5, ClF57, IBr3. So all these are called as what? It's over, right? For you, a P block is over.
Yes, sir, it is.
So then you should be able to answer this question. Okay, I suppose no one knows. Okay, they are called as interhalogen compounds. Hope you remember, right? So what do you mean by interhalogen compounds? Basically, if you have more than one type of halogen present in the compound and they make a compound, they make a molecule, those are what are called as interhalogen compounds. So all the ClF3, IBr3, AClF7, all these things, right, are what are called as interhalogen compounds. Okay, cool. So what is the time? 5 more minutes. Cool. Now what I want you to do now is I want you to draw the Lewis dot structure for I3 minus. I'll give you 2 minutes time. All right, 2 minutes is too much, but still, I'll give you 2 minutes time. So I want you to draw the Lewis dot structure for I3 minus. Let me see, and obviously I will draw it, and you can check whether you got it right or not. Go for it. I3 minus. I3 minus, ClF2 minus, all of them will have same Lewis dot structures, right? Go for it. Oh, this is Cl. It should be yeah, ClF2 minus. Correct. 3 halogens. Here also 3 halogens. Okay.
Sir,
Yeah.
we can actually draw it on your screen, sir. Can I?
Yeah, I will draw it on my screen. Definitely. I'm just giving you time
No,
to
we can
for you
also
to do
draw
it.
it on your screen.
Oh, you can draw it on your screen. Wonderful. You can share the screen and show me. Why not?
No, on your screen, sir. I'm drawing.
Oh, on my. How is it possible?
There's an option called annotate from Zoom.
Oh, annotation. Oh,
Yes.
oh. Okay. Understood. Okay. Hi. Yes, Srivatsan. Yes, I'm seeing it. Okay. New thing I have learned today. Nice. Thank you. Yeah, but if everybody draws on my screen, it'll become clumsy. I think it's better that you draw it on your paper. Oh, that's why I was thinking. When I was taking this 11th class, I was seeing suddenly out of nowhere heart and symbol and so many. I was like, what the dash is happening? I was like, where it is coming from? And now I understand. Thank you so much. Okay. Oh, maybe this will be very useful when you want to ask doubts, particularly, sir, this particular point, something like that. Yes, I understand. Okay. Right. So hope you have drawn it. I will draw it on this. I'll draw it now. Okay. Right. So I3 minus, we can understand that there are going to be 3 iodine atoms, and one of them is going to have a negative charge, and the other 2 are going to be neutral. Is that cool? Right. So let me draw that. 1 I minus, 1 I, and another I, which is neutral. Okay. Fine. So how did I come up with I should have the neutral atom only, neutral iodine only to be in the center? Because it comes when you go for the Lewis dot structure, making sure that all the things are getting paired, you will understand how is it. Okay. So iodine atom has 7 valence electrons. So 1, 2, 3, 4, 5, 6, and 7. Oh wait. Or let me for my this thing, I'll just put it like this. Okay. Right? So there is 7 electrons, and this iodine also has 7 electrons. 1, 2, 3, 4, 5, 6, 7. Okay, and this iodine atom will have 8 electrons in the valence shell. Already it's I minus, right? So 1, 2, 3, 4, 5, 6, 7, 8. Right? Okay, so 8 electrons, right? Okay. Now for these 2 iodines, it's pretty simple. Both these iodines require 1 more electron to satisfy its octet. So this will take 1 electron, and this will take another electron. Done. This is done, right? But still, I have to make sure that this iodine is somehow bonding. What do you think is going to happen? How is it that the third iodine atom is going to get bonded to the central iodine? Single electron will get shared. If single electron is shared, say I have this also going there, and that is going to become unstable. See, and the one more thing is that iodine is already stable. I minus is already having 8 electrons. So what other things can you think of?
Sir, the central iodine atom can get 1 electron from the negative iodine atom.
1 electron from the negative iodine. That makes how to put it? That makes I have 9 electrons on iodine. See, remember, odd electrons on any atom is really unstable. Okay. Any other thing can you think of? Hope I answered your question, right? If I put 1 electron on the central iodine from the side iodine, the central iodine will have 9 electrons. That is really unstable. Odd number of electrons is always unstable. What other things can you think of? Okay, I'll not take much of your time. The answer is it's going to be a coordinate bond. That's how it is, right? So if I draw a structure, I have I, and another I, and this is going to be a coordinate bond. That's what. And if you have to make sure that the lone pairs are also present. 1, 2, 3, 4, 5, 6, and other 2 electrons are involving in the coordinate bond. Oh God. Okay, I'm sorry about the background noise, people. Right, so there are 2 electrons here, and there are 3 lone pairs here. So obviously, this would have been the Lewis dot structure for I3 minus, and obviously it is going to be linear, right? So you can understand how is it linear. I have 2 bonding. Oh, there should be 3 lone pairs. Oh yeah, 3 lone pairs. One more lone pair is also here, right? There's, so you can see there are 3 lone pairs, right? Okay, so you have 3 lone pairs and 2 bonding atoms. Obviously, it fits your AB2L3, right? So again, I3 minus. If someone asks you what is the shape is going to be linear, and the geometry is still going to be trigonal bipyramidal. Okay, so let me stop with this, people. Any questions you want to ask me? Any questions? I'll give you maybe a minute. Any questions?
Sir,
any
why
doubts?
can't we?
Hmm.
So why can't we
can't we?
put the minus on the central iodine atom?
Okay, we'll try that. If you want to try that, check. So if I have I minus here in the central iodine, already it has 8 electrons, no? Right? So there's no way that it is going to get shared. There is no way that this is going to share electron with these 2 iodines. That's not possible. Yes?
Okay, sir.
Understood?
Yeah, understood, sir.
Okay. Any other question? Okay. So I suppose there are no other questions. Oh, okay. So yeah, so that says no question. Okay, good. Right. So people will meet. I think, guys, I will be requiring an extra class on Friday, like coming Friday. So you will have classes on continuous 3 days, Friday, Saturday, and Sunday. And don't worry, it is going to be only 1.5 hours. Okay, I'll not take 2 hours. So why? Because last week. Okay, no doubts. Fine. So last week I missed both the classes because there are certain things happen in my family. But anyways, so we'll try to compensate it, right? So now today half an hour got compensated. I still have almost like 2.5 hours of still compensation required, right? And obviously people at the more and more we go towards the exam, that is maybe now this is November, say from December onwards, I have to increase the number of classes because there is no way that I'll be able to complete the entire syllabus. Like, see, I can complete the syllabus very, very simply, right? But if I want to do justice to me, and if I want to do justice to you, right? So definitely, I have to take extra classes, and I really need your cooperation. I know that you have your board exams, you have all the other stuffs, you have your practicals coming and stuff. But yeah, this 1 year, this next 6 months, 4 months will be hectic for you, right? Be prepared for it. And see, now at least you what to say, you started a little late, so you have to put more attention to JEE if you really want to crack it. And I see everybody has good potential here, right? Everybody is having actually good potentials here. So it's like, even if you don't prepare, I would say you'll be able to easily clear the exam. Clearing the exam is not what we want, right? You have to get a good rank, right? And for that, it's high time. I don't know how many of you started practicing problems. If not, it's really high time that you practice problems. And each subject has to be given at least 2 hours. So basically 6 hours exclusively for JEE. You have to study if you really want to get a good rank, right? So anyways, thank you so much. We'll meet again on Friday. I will inform Akila also, right, that I'll be needing extra class, right? So thank you so much, people. We'll meet again.
Thank you,
Sir.
sir.
Yeah.
Thank you, sir.
How viable will be the January attempt, sir?
No, Kana, like I would say January will not even happen. Don't worry. That is what is my prediction is. There will be
Okay,
only
so-
one attempt this time. Yeah, I'm not sure, but that's what I am thinking.
In case there are 2 attempts, how prepared will we be for the first attempt, sir?
How prepared will you be for the first attempt? If you ask, like you are asking with respect to me, how much portions if I complete?
Yes, sir. Yes, sir.
I would have completed at least all the important chapters, right? From wherever you're going to get maximum number of questions, that chapters would have been completed for sure,
Okay, sir.
right? But again, it'll not be that much of a good attempt. But again, I would really suggest you to write it for sure, just to see how the exams are going. But your
Yes,
proper
sir.
attempt would be for the second exam. But I will make sure that you will be bloody prepared for those exams. That is my responsibility. Is that
Yes,
cool?
sir. Yes, sir. Yes, sir.
Right. Cool. Thank you, people. We'll meet again on Friday. Thank you so much.
Thank you, sir.
Thank you,
Yeah.
sir.
Thank you.